Hey guys, sorry, I screwed up on a reaction mechanism that I was showing you, so I had to clip it out and start over. So sorry about that. But what I was trying to do is I was trying to show you the formation of rhodopsin, and specifically how you get what we call that imine linkage between your aldehyde group of your 11 cis retinol and then also the amino group of your um, opsin. All right, so basically this is how it works. So let's say this is the aldehyde group of your retinol, and then we have opsin over here. All right. So basically, what happens here is that the carbonyl oxygen is going to grab a hydrogen from that NH3. Wow, that was ugly. I'm just going to keep drawing the aldehyde H the whole time, even though I don't have to, just to show you it never leaves. So once you protonate that oxygen, it's got 3 bonds, right? Which gives it a positive charge. That makes that carbonyl carbon really super duper sensitive to nucleophilic attack. And that's what the amino group in opsin can do. It can attack there, and it drives a pair of electrons up to the oxygen. Sorry, it's a little sloppy. That's an NH2 with a positive charge on it. All right, so now the opsin is bound to your retinol. All right, we're not finished with forming the linkage though. So this oxygen can then grab one of the hydrogens from the nitrogen. That forms water. All right, and what did we say about water all the time? It is a good leaving group. So it's going to leave, and at the same time, this pair of electrons on nitrogen can fall into a double bond. And then water can come back, grab that H, and that finishes off your imine linkage. And so that's the key linkage there. That's the formation that enables rhodopsin to be formed, and that's what this is. Okay, and you can see the full structure in your PowerPoint. So rhodopsin can actually interact with incoming light, right? So incoming light can be absorbed by rhodopsin. It actually will destroy this linkage right over here and your opsin ends up being recycled for future use. Also, energy is given off in the form of an electrical current that travels to your optic nerve and registers an image on your brain, or helps to register an image on your brain, or in your brain, sorry. So, pretty cool, pretty cool. I realize again that some of you may not feel confident in the organic mechanism part here. You may not have gotten to this in OChem. If not, please let me know. Just come by. I can show you. I can give you sort of the basics of carbonyl addition and then formation of imines as well. That's a common OChem 2 subject, and I can help you catch up on it if you need to. Okay, but yeah, vitamin D, vitamin A, essential for vision. Vitamin D First of all, there's lots of different forms of vitamin D. Probably the one that we are most familiar with is called vitamin D3, which is also known as cholecalciferol. And so vitamin D is actually a straight up derivative of cholesterol. You can see the process of how it's converted or how it's used here in this particular reaction scheme here. You have an enzymatic reaction that causes cholesterol to derivatize and form something called 7-dehydrocholesterol. And then this intermediate interacts with UV light. And you see when it interacts with UV light, you end up having one of those rings split open. And that is actually the formation of the vitamin D3 or cholecalciferol. Now, what's cholecalciferol used for? Well, it's used for actually several different things. Probably the most notable functions are regulation of calcium and phosphorus within the body. If you have deficiencies of vitamin D3, there's certain conditions that you're more prone to. Several of these conditions relate to the bones, right? Because calcium metabolism is important to bone strength, bone structure, and function. So if you have a deficiency of vitamin D3, you can get a condition called rickets. And this is not something you see a lot nowadays, but in older times, when people had problems with not vitamin D3, but with their calcium intake, not getting enough calcium, they would often develop rickets. And so the most common symptom of somebody having rickets is bow legs. That's where the legs will actually they'll sort of bend out and sort of develop sort of a bow-like structure. And so if you have somebody that has this condition, a lot of times they're referred to as being bow-legged. Look it up if you want to see pictures. There can be minor forms of this and major forms, but back in the days when it was hard for people to get good sources of calcium, before the process of pasteurization of milk, then this was more of a problem. Now, not so much, but it can happen if you have either a deficiency of calcium or a deficiency of vitamin D3. Another thing that's associated with a vitamin D deficiency is depression. Specifically, you see this a lot of times in winter when, let's say you live in a cold, snowy place, you're not able to get outside nearly as much, the sun isn't shining nearly as much, you're stuck inside, and some people get kind of sad when this happens. And there's actually a neurochemical reason for this. It's called seasonal affective disorder. You may have heard of it. Seasonal affective disorder. Great acronym for this is SAD, SAD. So how appropriate, right? And what causes seasonal affective disorder? Well, if you look in the pathway down below, you see that for the formation of vitamin D, you gotta have ultraviolet radiation. Where do you get most of your UV light from? The sun, right? So if you're not getting enough of this, you're not getting enough sunlight, not getting enough of the UV rays, then you might have some deficiencies in your vitamin D3 levels. And one of the things that vitamin D is important for is stabilization of mood. It can be one of the many factors that can affect mood and cause depression, right? So one of the common prescriptions that people with seasonal affective disorder have is actually not for a supplement, a pill, a medication like that, but it's actually for a UV lamp that they can put in their homes to literally either sit in front of or lay in front of so that they can get the UV radiation that they would be getting from the sun. So, kind of interesting. There's a similar type of vitamin D. It's called ergosterol. That has been looked at as a possible analog and a treatment for vitamin D3. I don't know. Honestly, since I wrote this, I haven't kept up with the research, so I don't know if it's been that effective or not, but it would be a good thing to look up. All right, vitamin E. Vitamin E is an antioxidant. Ooh, there's that buzzword again, nutritional buzzword alert. Antioxidant. Much like glutathione we saw before, the important peptide, vitamin E can help to sort of take one for the team. It can react with a lot of these oxidizing species that are present within the body that can harm biomolecules such as nucleic acids and proteins. Instead, if they interact with vitamin E can react with them, and so that's important. That helps prevent a lot of our biomolecules from taking damage. It will act as an antioxidant and a radical scavenger, and so as a result, it prevents us from having certain types of conditions, diseases that are commonly caused by harmful oxidizing agents, most notably cancer and muscular dystrophy. And that's the structure of vitamin. All right, and then we have vitamin K. Vitamin K is important in blood clotting. And so, if you remember, we've gone to this a couple of different times, but I showed you previously, I talked about the blood clotting cascade, right? I showed you the diagram that has all those many factors that are involved in the formation of blood clots. Vitamin K is going to be one of the most important factors. Vitamin K is one of the activators of thrombin, right? If you remember, thrombin was an important enzyme to help activate the zymogen fibrinogen, and then fibrinogen, once it became fibrin, that was the one that specifically caused the clotting process. Well, in order to get to fibrin, we need thrombin, but in order to get thrombin, we got to have vitamin K, right? So thrombin actually exists as a zymogen, prothrombin, and it's not activated until you have the action of vitamin K and other factors to get it out of its zymogen form. But once it forms thrombin, then it can activate fibrin and complete the blood clotting process. Here's the structure of vitamin K. I'm not concerned about you knowing the structures, by the way, of these. I was just kind of showing you to sort of illustrate the fact that there are a number of conjugated parts of these molecules, and you can see how they would be lipid soluble and not very water soluble. This picture shows really how vitamin K, or what vitamin K acts upon. Basically what it does is it's going to act on the glutamic acid residue of a prothrombin, and it essentially adds a carboxylate group. Right? You can see that one of those carbons, middle carbons in the glutamic acid residue prothrombin now has two carboxylate groups instead of just one, and that allows it to bind to calcium. Calcium is what we call a bidentate ligand. Don't worry about it if you've never heard it before. That's from a sort of an analytical chemistry term, right? But in order to bind that calcium, you got to have two carboxylate groups, and so that's not possible without vitamin K. All right, last groups I want to mention are ones that are called prostaglandins. Prostaglandins are derived from a little molecule called arachidonic acid. And so you can see here that top structure is arachidonic acid. It's got two areas of conjugation, right? And so prostaglandins basically have this base structure, and then they also contain a 5-membered ring. There's several different types of prostaglandins that are made. These help to control a lot of sort of the internal physiological functions. They are one of the factors involved in controlling blood pressure, smooth muscle contraction, prevention of blood clots, induction of inflammation. They're a very important sort of immune system lipids. A subgroup of these is called leukotrienes. They're kind of similar to prostaglandins, except that instead of having the ring there, oops, sorry, I keep getting confused by the fact my PowerPoint gets cut off and the iPad, so I'm having to look at the computer here. So they're kind of similar to prostaglandins. You don't have a ring, but instead you have a triene portion. And it's cut off here, but you can see there's a conjugated triene that's present, and there's always a characteristic cysteine residue that's coming off. These groups do much the same thing that other prostaglandins do, but also one important one I'll highlight is the role they have in asthma. It is possible to have too much of one of these, right? If you have an overload of leukotriene, I think it's leukotriene C, that actually can make you extra hypersensitive to invading antigens and can cause sort of a triggered immune response. And that's bad in a lot of cases. And so in the role in asthma specifically, if anybody has ever had asthma, you kind of know the symptoms. You oftentimes experience a shortness of breath. You can't really breathe very well. Your smooth the muscles, your lungs are very much constricted, and the muscles around your lungs are very much constricted in your throat. You can't get in there, so you have to have an inhaler. And basically what you're doing when you inhale is you're inhaling something that can sort of deactivate the role or the action of these leukotrienes. All right, so very important in regular function, but it goes to show that with any biomolecule, having an excess of it can lead to some problems. All right, so I'm going to wrap it up there. That finishes chapter 8. Next one is going to be chapter 16. We're going to skip all the way to 16. That's going to be carbohydrates, aka sugars. All right, till next time. Talk to you later. Bye-bye.